Hey everybody, welcome to this tutorial. What we're going to be doing today is looking at how to do just a one-way ANOVA or univariate ANOVA in JASP. Files that you're going to need, you're going to be able to find on the website or directly below here in the comments. Alright, so let's get to it right away. We're going to be asking the question about NHL player spending. And the data that we're going to be using is the NHL salaries top 10 from seasons 2017, 2018, 2019, and 2020-21. So what we're going to be doing is importing that data firstly into JASP. So the way we do that is we open up the file here, we ask for our file, which I've called NHLsalaries.csv. So we're just going to open that file, and we see it opens it up quite nicely. We've got our player rank, we've got the name, we've got season, and then we've got salary in millions of dollars. So in order to do a one-way ANOVA, simply we go up to ANOVA, click on that, and just select under Classical ANOVA. That opens up this side panel, and what we're going to do is select our dependent variable, which is salary in this case. Then we want to select our fixed factor. Our fixed factor is simply going to be season in this case. And we can see here it's going to calculate our ANOVA table. And we get a mean square of 12.54, an F ratio of 5.12, and a p-value is equal to 0.005. Simple. That's it. That's your ANOVA. So what we've got is our sum of squares of our model and our sum of squares of our error term or our residuals down here as well. So there's a few more things in JASP that we can do. So for example, if I simply just click on descriptive statistics, now I've got my mean standard deviation in N for each of the 4 seasons. Another thing I could do is ask for an effect size. So in this case, it's given us eta squared, which is basically just R. It's the same idea. So it's the amount or the proportion of the variance, of the total variance that is attributable to the model. So if we added up our total variance, which is the sum of squares of the season and sum of squares of the residual, and we look at the sum of squares as a proportion of both, that comes up to 0.299. Now, when we do that with multiple factors, we might use partial eta squared. But in this case, we see that's the same value because there is no partial. We only have one factor in this case. Okay, so another couple things we could do is click on assumption checks. So we could look and ask for homogeneity of variance tests. And what we see, we have no real problem with that. Our p-value is 0.69. If there were, we can select Brown-Forsyth or Welsh-corrected values, but we don't need those because our homogeneity or equality of variance is not being violated in this case. So I'm going to unselect those. The other thing we can do is we can select the QQ plot of our residuals. Remember that our residuals should be normally distributed. And we see here, if we look at the QQ plot, there seems to be a little bit of deviation here around the middle. But overall, it's lining up fairly closely along these lines. Okay, so we know that there's a difference somewhere in between the seasons. We just don't know which season is different than which. Therefore, we can run some post-hoc tests. So I'm going to select under post-hoc tests, scroll down and click on season and put that in. Now, I can select a few different types of post-hoc tests. The most common that you might come across would be a Tukey post-hoc test. So we see we've scrolled down here and selected Tukey by default, and we see we have some contrasts down here at the bottom. So 2017 compared to 2018 is a mean difference of 1.14. Remember, that's salary in millions. And our P of our Tukey corrected multiple comparisons shows us that our p-value is 0.376. Now, if we look down here, the only one that is significant at the p less than 0.05 level is 2017 to 2019. We look at that and we see that that is the one that's different. So the other thing I could do is select Scheffé or Bonferroni or even Home Bonferroni. And we see that essentially it comes across the same value. It's only that one that seems to be different. So it doesn't really matter in this case which post-hoc test you've used. In this case, perhaps if we want to be more conservative, we'd use a Bonferroni post-hoc multiple comparison correction. But there's lots of different reasons for picking different ones, and you can look at other videos to find out why you would pick certain post-hoc tests in certain situations. So I can flag significant comparisons as well in those, and that just shows me that it gives me stars across the different ones that are significant, and we know that that's the only one is the difference between 2017 and 2019. If I select under my descriptive plots and I put season onto the horizontal axis, that creates a new plot for me where I see my differences or my values. And this is where we can see 2017 is different from 2019. This gives us a nice graphical representation of that. I can display error bars with 95% confidence intervals as well. That gives me another idea of how well my data fits my hypothesis and what differences seem to be, or which comparisons seem to be different. Other than that, if we wanted to, if we found that our data is not normally distributed or we've got other problems with the assumptions underlying ANOVA, we might want to use a Kruskal-Wallis test to do a non-parametric test. We'll get into that at a later video. And that's it for doing this in JASP. Hopefully that gives you a better idea of how to do univariate one-way ANOVAs in JASP.